So for today's session, we'll be looking at some algebraic properties of matrices, and then we will define what we call inverse of a given matrix, if it exists. Okay? So let's start with these properties. So I am now showing you all the properties that we will use in this course. And these properties, they should look familiar to you because these properties are some of them, okay, or actually most of them are um, similar to the properties of real numbers. For example, for letter A, you have A plus B, this is equal to B plus A, okay? So meaning you can interchange the addends and the resulting matrix should be the same. Okay, and um, before I enumerate some or all of these properties, let me just remind you that these properties works provided that the operations works. Okay, for example, what I'm saying is that if you add the two matrices, of course you are assuming that they have the same sizes. Okay, if you multiply matrices, you are assuming the condition that the number of columns of the left factor must be equal to the number of rows of the right factor. Okay? So the operations on the matrices must be valid. Okay? Okay. So as I mentioned, this guy here, if you add two matrices A plus B or A and B, A plus B will just be the same as B plus A. So you can interchange them, and that's called the commutative law for matrix addition. And then if you have three matrices and you add them, so A plus quantity B plus C, it will be the same as A plus B, and then you add plus C. Okay? So you can regroup. You can regroup the addends. Okay. So this is called the associative law for matrix addition. Now for the multiplication, we have something like this. So in here you have matrix A, and then you multiply it to the product of BC. Okay. The product BC. This guy here is the same as you multiply first AB, then multiply C on the right. So you can also regroup, okay, provided that the arrangement of the matrix like this, ABC, this is still ABC, so you can regroup, okay, and you will get the same answer. So this is the associative law for matrix multiplication. Now, there is no commutative law for the matrix multiplication. As you can see, A and B, I had commutative law for matrix addition and then associative law for matrix addition. But for letter C, we immediately state the associative law for matrix multiplication. That's because there is no commutative law for matrix multiplication. And I will I think I mentioned this in the last lecture, but anyway, I'll say it again. This guy here, AB, may not be the same as BA. Okay, so in general, AB may not be the same as BA. Okay, and then we have from D until G. These are called the distributive laws. Okay, so in here you have A times the quantity B plus C. This is equal to AB plus AC. And notice that your A here, it's a left factor. And then your B plus C, they are right. This is a right factor. Okay? The B plus C is a right factor. A is a left factor. So when you distribute this matrix A over this sum, the A must be left must be retained as left factor. For example, in here you have AB, okay? And then in here you have AC. So A is always on the left, okay? So when you distribute this, you have to retain the position of the matrix being distributed. That's called the left distributive law. And in here you have quantity B plus C, and then you multiply A on the right. So if you distribute this A over the sum, the A must be on the right. So in here you have BA, and then plus you have your CA. And that's your right distributive law. Okay? And of course, instead of addition, you have subtraction here and subtraction here. So um, similar property. Okay, instead of adding them, you have subtraction. You have subtraction in here. Okay. For H and I, this is also distributive law, but this time the one you are distributing is a scalar. Okay, so you have the sum of the matrix B plus C, and then you have a scalar A, you just distribute it. Okay, so if you distribute it, you have AB plus AC. And then, of course, if you have subtraction, same principle for as in letter H. Okay, letter J. This time you have two scalars being added, and then you multiply the matrix C. So this time your matrix is being distributed over the sum of these two scalars. So you have AC plus BC. And similarly, if you have subtraction for letter K. Okay? And then for L and M, let's start with L. In here, you have two scalars, A and B. The scalar B is being multiplied to C. Okay? So you will still get a matrix here. And then you multiply the scalar A. This is the same as multiplying the two scalars first. So you multiply AB, and then you multiply this scalar AB on the matrix here. Okay, so you can regroup them. So either you multiply first the one of the scalars to the matrix before multiplying the other scalar, or you multiply the two scalars first before multiplying it to the matrix. Okay, and then lastly, this time you have two matrices BC, okay, B and C, and then you multiply them, you'll get a matrix. And then you have the scalar A, you multiply it to the product BC. This will be equal to multiplying the scalar first to B. So you have this before multiplying it to the matrix C. Or you can just first multiply the scalar to the matrix C, okay, before multiplying the matrix B. Okay? But keep in mind, again, you have the product BC. B is a left factor, C is a right factor, so the B should always be on a left factor. So like this, B is on the left of C. In here, B is still on the left of C. Okay? So these are the properties of the operators, the addition and subtraction and multiplication, scalar multiplication as well for the matrices. Okay? So let's look at some examples here. Let's have the matrix ABC here, and then we want to find first the product AB. So in the next example, in the next few slides, we'll be practicing our matrix multiplication. And of course, as we will be checking the properties of matrices that I have enumerated in here. Okay, so let's start. Let's find the product AB. So we will have 2, -3, 4, 1. You multiply this to the matrix B, you have 4, negative 1, 1, 1. Okay? So this is equal to. So first row, 2, negative 3. Let us multiply to the first column. So first row, first column. So in the product, it will be in the entry 1, 1. Okay? So you have here 2 times 4 plus negative 3 times 1. So first row, first column, 1, 1 entry. Now, let's have first row, second column. That means the sum and product will be on the 1, 2 entry. So first row, second column. So 1, 2 entry. So we have 2 times negative 1 there. 2 times negative 1 plus negative 3 times 1. Negative 3 times 1. So that's first row, second column. Now, we have second row, first column. It means we will be on the 2, 1 entry. Okay, 2, 1 entry. Second row, first column. So in here, we have 4 times 4 plus 1 times 1. And then lastly, we have second row, second column will be at the 2, 2 entry, or we'll get the 2, 2 entry. So we have 4 times 1, 4 times negative 1. So 4 times negative 1 plus 1 times 1. Okay? And we can simplify this. Let's do this. You have 2 times 4, that's 8 minus 3 here. So we have 5. In here, you have 4 times 4, that's 16, plus 1 times 1. So we will get 17. In here, you have 2 times negative 1, that's negative 2, plus negative 3 times 1, that's negative 3. So we will get negative 5. And then in here, you have 4 times negative 1 plus 1 times 1. We will get negative 3. So this is the product A, B. Okay? Next, here, this time we want to get the product BA. Okay? So before we have AB, and then we have BA. And then after getting the product, let's check if AB equals BA. Okay? So this guy here, this time, you have 4, negative 1, 1, 1, multiplied to 2, negative 3, 4, 1. Okay? So first row, first column, we have 4 times 2 plus negative 1 times 4. Then first row, second column, we have 4 times negative 3 times 4 times negative 3 plus negative 1 times 1. And then second row, first column, we have 1 times 2 plus 1 times 4. And then second row, second column, we have 1 times negative 3 plus 1 times 1. So if we simplify this, we'll get, we have 4 times 2, that's 8, plus negative 1 times 4, that's minus 4. So 8 minus 4, that's equal to 4. And now, notice, the entry here, the 1, 1 entry, it's 4. While this guy here, the 1, 1 entry, it's 5. So definitely, they are not equal. The AB here is not equal to the BA. Okay? Then let's finish this matrix. Here you have 4 times negative 3, that's negative 12 plus negative 1 times 1, that's negative 13. Okay, negative 13. And then here we have 2 plus 4, that's 6. Here we have negative 3 plus 1, that's negative 2. So this is the product BA. Okay. Next, here we have A times B minus C. So let's start with B minus C first. Anyway, let's write the matrices here. So A will have 2 minus 3, 4, 1, and then times B minus C. So 4 minus 1, 1, 1, minus. We have 0, negative 1, 1, 1. Okay? Then we copy A first. 2 minus 3, 4, 1. And then for this guy, we will have 4 minus 0. That's just 4. Negative 1 minus negative 1, that's 0. 1 minus 1, that's again 0 here. And then 1 minus 1, that's again 0 here. So if we multiply this, we will get, so first row, first column, we have 2 times 4. Let me write it as 8 plus negative 3 times 0. So that's 0. So we'll just have 8. And then first row, second column, we have here 2 times 0 plus negative 3 times 0. So that's just 0 here. Second row, first column, we have 4 times 4, we have 16. And then 1 times 0, that's just 0. So we'll just have 16. And then second row, second column, we have 4 times 0. That's 0. And then plus 1 times 0, again 0. So we have this matrix here. Okay, so far so good. Next problem here. So AB, we have AB in here. 2 minus 3, 4, 1 times the B. We have 4, negative 1, 1, 1. Then minus AC, 2, negative 3, 4, 1 times 0, negative 1, 1, 1. For the AB, we already have this. So let me get that AB. This was our AB. 5, negative 5, 17, negative 3. Okay? So we have here 5, negative 5. Sorry, 5 here. 5, negative 5, and then 17, negative 3. Let's re-verify that. Okay. So 5, negative 5, 17, negative 3. And then for the AC, let's calculate. So here, minus 2 times 0, that's 0. Negative 3 times 1. Okay? So negative, so 2 times 0, and then negative 3 times 1. So we have here negative 3. And then first row, second column, we have 2 times negative 1. Okay, let me write that. 2 times negative 1 plus 3 or plus negative 3 times 1. Then second column, first row, we have 4 times 0 plus 1 times 1. So we have 1 in here. Then second row, second column, we have 4 times negative 1 plus 1 times 1. Okay? So in here, let's copy first 5, negative 5, 17, negative 3, and then minus. We have here negative 3 and then 1 here. And then for this, we have negative 2 plus negative 3, that's negative 5. Then here, negative 4 plus 1, that's negative 3. So if we simplify this, we have 5 minus negative 3, that becomes 5 plus 3, and that's 8. You have here negative 5 minus negative 5, that's 0. Here 17 minus 1, that's 16. Then finally, you have negative 3 minus negative 3, that's 0. And observe, this is this guy here. Okay? 8, 0, 16, 0. So A times B minus C, it's the same as AB minus AC. So the distributive law. Okay? Questions so far? For this, let's have A times BC. So we have here, you have A first, 2, negative 3, 4, 1. And then you multiply BC. So 4, negative 1, 1, 1, multiplied to 0, negative 1, 1, 1. So you start with BC. So this guy here, it's 2, negative 3, 4, 1. And then for the BC, we have 4 times 0 plus negative 1 times 1. That's negative 1. And then here you have 4 times negative 1 plus negative 1 times 1. And then here we have 1 times 0 plus 1 times 1. So you have positive 1. Then 1 times negative 1 plus 1 times 1. And then we simplify this. So we copy A, 2, negative 3, 4, 1. Here we have negative 1 and 1 in here. Here you have 4 times negative 1, that's negative 4, plus negative 1 times 1, that's negative 1. So you'll get negative 5. In here you have negative 1 plus 1, you'll get 0. And then let's multiply this. 2 times negative 1 plus negative 3 times 1. So first row, first column. And then first row, second column. 2 times negative 5. And then negative 3 times 0. So I'll just write 2 times negative 5. Second row, first column, 4 times negative 1 plus 1 times 1. Sorry, that's second row, first column. And then second row, second column, we have 4 times negative 5. So if we simplify this is negative 2 plus negative 3, that's negative 5. Here we have negative 10. Here negative 4 plus 1, that's negative 3. Then here 4 times negative 5, that's negative 20. So this is A times BC. Okay? And then I want you to verify that if you started with AB first and then multiply BC, you should get this same answer. Okay? You already have the value for AB from the previous example, so you can just copy that. Well, at the beginning, of course, you copy all these matrices. Okay? So let me do that. You have here matrix A, 2, -3, 4, 1. Multiply this to 4, -1, 1, 1. And then you multiply matrix C, 0, -1, 1, 1. So you already have the value for this, and then just multiply that value with this matrix, and then you will have a final answer. Okay? And therefore, you will get, or you should get, this guy here. Okay? Questions? Okay, so these examples, your matrix multiplication is used a lot of times, so I hope that gives you a good practice on matrix multiplication. Well, at least for 2 by 2 matrices times 2 by 2 matrices. Okay? Then, let's have this definition. The zero matrix. We sometimes denote it by 0, or if we want to specify the size of the matrix, we put the subscript m by n. So basically, the zero matrix, it's the matrix whose entries are all zeros. Okay, that's why it's called the zero matrix. These are the properties of the zero matrix. Okay, so provided that all operations here are well defined, okay, then if you add any matrix to the zero matrix, you should get the matrix. If you add a matrix A to the zero matrix, you should get A. Okay? So A plus 0 equals 0 plus A, which is equal to A. And then here you have A minus the zero matrix, that's equal to A. Okay? So A minus the zero matrix, that's equal to A. Of course, 0 minus A will be negative A. Okay? So maybe I can include that here. 0 minus A, this is equal to negative A. So you negate all the entries of A. And then, of course, if you subtract A with itself, okay, you should get the zero matrix. So A minus A, this is defined as A plus the negative of A, that should give you 0. Okay? Now, if you multiply the scalar 0, the real number 0, if you multiply it to any matrix A, you should get the zero matrix. Okay, if you multiply the scalar 0 to any matrix A, you should get the zero matrix. Now look at this. Okay, if you have something like some scalar multiplied to a matrix and you got the zero matrix, okay, then at least one of these is true. Either your scalar was 0, okay, that's the number 0, or your matrix is the zero matrix. Okay, So your scalar is 0, your matrix can be any, or you have any scalar but your original matrix was the 0 matrix. Okay? So if C A is equal to the 0 matrix, then C is the 0 scalar or A is the 0 matrix. Very much similar to the space of or to the set of real numbers. If you got two, so let me just recall it here. If you have real numbers like, so if x, y are real numbers, so if x, y are real numbers, let me just fix this guy. So so if x and y are real numbers such that when you multiply them and you get the 0, so x, y equals 0, then at least one of them is 0. So either y is 0 or x equals 0 or both of them are 0. Okay? So very much similar to this property. Okay? Next, if you have these matrices A, B, and C, okay, such that the product of AB equals the product of AC, it does not mean that B and C are equal. Okay? If A, B, and C are matrices such that AB equals AC, it does not mean that B equals C. This means that there is no cancellation law in the multiplication of matrices. So for example, you have these three matrices, okay? We have here, obviously you see B and C are not equal, okay? They have, you have here 1, but here 2. So they are no longer equal. But let's check. What is AB? So what is AB? We have here 0, 1, 0, 2. Multiply it to the matrix B. We have 1, 1, 3, 4. So this is equal to, so 0 times 1. So 0 times 1, that's 0. 1 times 3, that's 3. Then 0 times 1, that's 0. 1 times 4, that's 4 here. Then 0 times 1, that's 0. 2 times 3, that's 6. And here you will get 8. So this is your AB. AC, if you try to multiply this, you will get the same. Okay? Sorry, that's the C. I have to put the A first. So this is your A0102. So if you try to do this, you will still get 3, 4, 6, 8. Okay? So this means you have AB equals AC. But as you can see, B is not equal to C. Okay? So no cancellation law. No cancellation law. Okay? Unlike in the set of real numbers, you have cancellation law. But for matrices, we don't have that. Okay? And in here, we are talking about multiplication. Question. Next, if you have two matrices, okay, if you have two matrices and the product is equal to 0, it does not mean that A equals 0 or B equals 0. Okay? You can have two non-zero matrices. When you multiply them, you'll get the zero matrix. Okay? So for example, in here, you have A. Here, it's a non-zero matrix because there are non-zero entries. Same is true with B. But if you multiply AB here, if you multiply AB here, you have 0, 1, 0, 2, multiply to 1, negative 1, 0, 0. So here you have 0 times 1 plus 1 times 0, that's just 0. Same is true with this guy, 0 times negative 1 plus 1 times 0, that's 0. And in here, you have 0 times 1, that's 0, plus 2 times 0, that's 0, and also in here. So the product AB, it's the 0 matrix. And then you have non-zero matrices. Okay? Sorry, the product AB, it's equal to 0, but you have non-zero matrices. Okay? Questions? Next, let us define what we call an identity matrix. Okay? So, the identity matrix, which we will denote by I or IN, I subscript N, this is as the square matrix. Take note, identity matrix, square matrix, whose entries in the main diagonal are all 1, while the rest are all zeros. So remember, main diagonal, okay? This is your main diagonal. So for the identity matrix, you have all these equal to 1, but the rest are all 0. Okay? So identity matrix. So take note, identity matrices, they are square matrices. Okay? So we sometimes denote it by I if we don't care about the size, but if we need the size, okay, we just put the subscript. Okay? Now, a beautiful theorem in relation to the identity matrix is the following. If A is an M by N matrix, then A times IN, it will give me A back. Okay? So take note, my IN here, it's on the right of A. Okay? The other guy here, you have IM times A, it will give me A back. And take note, here I multiplied on the right a matrix of size n by n, the square matrix with size n. On here, on the left, I multiplied the square matrix of size m. So different identity matrices if your m and n are different. Okay? And take note that the multiplication here It makes sense because your A, it's m by n. Your in, that's n by n. So if you multiply them, you should get m by n. Okay? On the other side here, your im, it's m by m. And then your a, it's m by n. So if you multiply them, you should get m by m by n. So m by n. Okay? On the other hand, if your A is a square matrix, let's say it's an n by n matrix, then you have this beautiful equality. So A in, that's the same as in A, and if you multiply them, that's equal to A. So A times in, that's A. In times A, that's A. So this is one of those cases um, where you can interchange the left factor and the right factor. So if one of your factors is the identity matrix and you have a square matrix being multiplied to that, then you can interchange. Okay? Okay. Now, we are ready to define what we call the inverse of a matrix, if it exists. So, let A be a square matrix. And suppose we found another matrix B, the same size as A, okay, such that if you multiply AB, okay, or you multiply BA, you get the identity matrix. Okay? So you start with a square matrix A, and then you found another matrix B, the same size as your A, such that when you multiply AB or you multiply BA, you get the identity matrix. Okay? Then we say A is invertible, or A has an inverse, or A is non-singular. Okay? And we call B the inverse of A. And we write it this way. B equals A superscript -1. Okay? So first, this guy here, this is not 1 over A. In fact, we don't have this. Okay? This notation here, we are not going to use this. Okay? This will not make sense for us. So don't write the inverse of A as this guy. And therefore, some students, okay, think that there is a division on matrices. So for example, when they see, say, C A inverse, they write this, C over A. This does not make sense in the set of matrices. So we don't have this guy here. Okay? A lot of students write this guy here this way, and that is not valid. Okay? So again, you start with the matrix A, and suppose you found a matrix B the same size as A. Okay? So A is a square matrix such that the product AB equals the product BA equals I. Okay? Then we say A is invertible and B is called the inverse of A. And we write B equals A inverse. Okay? Now, take note that you started with B, with A here. Okay? So we are talking about A. If you started with B, then you also say that B is invertible and A is called the inverse of B. Okay? In fact, these two guys will be invertible. If you have a matrix A, square matrix A, you got another matrix B, the same size of A, satisfying this, then both matrices are invertible. Okay? Questions? Now, if you cannot find this matrix B with this property, if there is no matrix B, okay, then we say that A is not invertible, or we say that A is singular. Okay? So A invertible, non-singular. A not invertible, singular. Okay? So there is a question. I wrote earlier that AB does not equal BA in general. Okay? And I mentioned that there will be some set of matrices where the equality will hold. It's this guy here. It's this set. Okay? So you have a lot of matrices where AB equals BA. Okay? And you will have a lot of matrices, a lot of matrices where AB equals BA, and in fact, their product is I. Okay? And if that's the case, if their product is I, then we have singular matrices. Okay? You will be able to find such the matrices such that AB equals BA. This is fine. Okay? And you will be able to find some matrices such that AB equals BA and they are both equal to I, which is also fine. And you will be able to find a lot of matrices where AB is not equal to BA. So these are all possibilities. Okay? For this set, okay, we say that the multiplication commutes for this set of matrices. The one that satisfies, or the set of matrices satisfying this. Okay? And of course, those invertible matrices, they also belong to this set. Okay? And then you will have this set of matrices where you got AB equals BA equals I, the set of invertible matrices. Okay? But you will also have those sets, like I mentioned, that the matrices, when you multiply AB, it's not the same as BA. Okay, so do not be confused. That's why it is said in general, AB does not equal BA. Okay? Only the special ones where you have AB equals BA. And more special if your AB equals BA equals the identity. Okay? So that's a good question. Here are some remarks. If A and B are matrices such that AB equals BA, which is equal to I, then A is the inverse of B and B is the inverse of A. Okay? So A is the inverse of B. So A, this is the inverse of B, and also B is the inverse of A. Okay? So one is the inverse of the other. Take note that if this condition here is satisfied, then you have these guys here. Okay? Then, also, if A is invertible, then its inverse is unique. If you have a matrix which is invertible, then the inverse, it's just only one inverse. Okay? There will be no other inverses for that matrix. Okay? So the inverse is unique if it exists. Let's look at these examples. You have a matrix A here and a matrix B here, and we want to verify if they are inverses of each other. So what we actually want to do here, for the moment, take note of that, for the moment, we want to verify this guy here. Meaning, if we calculate the product AB, it must be equal to the identity matrix. If we calculate the product BA, it must be equal to the identity matrix. So we have to check both of them. Okay? So that's what we're going to do at this point of our lecture. Okay? So let's have AB. AB, that's 1, 3, negative 2, negative 5 times negative 5, negative 3 to 1. So if we do the multiplication, we have here 1 times negative 5, that's negative 5, plus 3 times 2, that's 6. And then for first row, second column, we have 1 times negative 3, that's negative 3, plus 3 times 1, that's 3. Second row, first column, we have negative 2 times negative 5, that's positive 10, plus negative 5 times 2, that's negative 10. Then lastly, negative 2 times negative 3, we have positive 6, plus negative 5 times 1, that's negative 5. And clearly, you will see here, this is 1, 0, 0, 1. So this is the identity matrix, the 2 by 2 identity matrix. Okay? And then let's check BA. So we have BA. So this time we have negative 5, negative 3, 2, 1, multiplied to 1, 3, negative 2, negative 5. So if we do this, you have here negative 5 times 1, that's negative 5, plus negative 3 times negative 2, that's 6. Then here, first row, second column, negative 5 times 3, that's negative 15, plus negative 3 times negative 5, that's positive 15. Second row, first column, 2 times 1, that's 2, plus 1 times negative 2, that's negative 2. Then lastly, second row, second column, 2 times 3, that's 6, plus 1 times negative 5, that's negative 5. So you will clearly see here that you have the identity matrix here. Therefore, A and B are inverses of each other. Okay? So A and B are inverses of each other. Okay? So again, at this point, we checked both A times B and B times A. And we showed that the products, it's the identity matrix. Okay? Later on, we will prove that we'll just have to check one of them. Okay? So later we will prove that one, that we only need to check one of them. And that's enough to say that they are inverses of each other. Okay? Question? Now, in here you have two matrices. Particularly, you have two 2 by 2 matrices, and you are asked to verify if they are inverses of each other. So our goal is, how do we find an inverse of a matrix if it exists? So suppose you are just given the matrix A. How do we find the inverse of that? So we will learn in this course how to obtain these inverses if they exist. In fact, we will learn also later how to identify if a certain matrix has an inverse. Okay? So we will have that later in our course. For now, let us have a 2 by 2 matrix. Okay? Suppose your matrix A is given by this. So A, B, C, D. Okay? Then this matrix A is invertible. Okay? If and only if this guy here holds. Okay? AD minus BC not equal to 0. Okay? So meaning, if A is invertible, this should hold. Conversely, if you have a 2 by 2 matrix that such that this guy here holds, then your matrix A should be invertible. Okay? So at least we have a criterion on how to determine whether a 2 by 2 matrix is invertible or not. You just have to calculate this guy here. Okay? Furthermore, since we already know that this matrix is invertible if it satisfies this, how do we get the inverse? We use the following. The inverse of A will be given by this. So 1 over AD minus BC. And this guy here, it's valid, meaning it exists because the denominator is not equal to 0. That's your condition here. So 1 over AD minus BC times this matrix. So what happened here? From the original matrix, A and D were interchanged. So this becomes DA here. And then B and C, they were negated. So negative B here, negative C here. You don't interchange B and C. You just put a negative. For A and D, you have to interchange. Okay? So again, if you have a 2 by 2 matrix given by this, then this matrix is invertible if and only if AD minus BC is not equal to 0. And in this case, the inverse of A will be 1 over AD minus BC times the matrix D, negative B, negative C, A. So diagonal entries were interchanged, and then you negated the other two entries. Okay? Now, this number here, okay, this number here is called the determinant of A. So determinant of A. And we denote the determinant by this, det A. Okay? So, this determinant, we will discuss this even further later in the course. But I am introducing it to you now, at least for this 2 by 2 matrix. Okay? So, what does this mean? This guy here and this theorem. You have a 2 by 2 matrix A. If the determinant of A is not equal to 0, then A is invertible. If the determinant of A equals 0, then A is not invertible. Okay? So let me just write that. A 2 by 2 matrix. Okay? So 1, if that A not equal to 0, then A is invertible. If that A is equal to 0, then A is not invertible. Okay? Question so far? Okay? So, again, you have a matrix, a 2 by 2 matrix, A, B, C, D here. You want to get the inverse. It will be 1 over AD minus BC times this matrix. Okay? Provided that this AD minus BC is not equal to 0. Okay? So, let's look at these examples. So, say this is our matrix A here. So, A inverse, if it exists, okay, let's start with the determinant of A. Determinant of A. So, you have this times this, okay? So, you get this, and then you have that. So, you have 3 times 1 minus 2 times 1. This is equal to 1. And therefore, A inverse, this is 1 over 1 times. You interchange the diagonal entries. You have 1 and 3 in here. And then you negate the other 2 entries. So negative 1, negative 2 in here. And of course, 1 over 1, that's just 1. So you have this negative 2, negative 2 here, and then 3 there. So this is the inverse of A. Okay? For number 2 here, let's say this is your B. Let's look at, or let's find the determinant of B. So this will be 2 times negative 1 minus 4 times 0. And this is just negative 2. So again, this determinant here, it's not equal to 0. So we can find the inverse of B. So B inverse. This is 1 over negative 2 times interchange. So this is negative 1 and 2. And then negate. Of course, negative 0, it's still 0. But here we have negative 4. So if we simplify this, if we multiply that scalar, we have 1 half 0. 4 over 2, that's 2. 2 over negative 2, that's negative 1. So this is the inverse of B. Okay? Questions? Okay. Next problem here. Consider the system. U equals ax plus by. V equals cx plus dy. Write x and y in terms of u and v. Okay. So in here, in the system, we will have written u and v in terms of x and y. So this time, we will try to isolate x and y and write the expressions in terms of u and v. So what we're going to do here is the following. We write this as a system of linear equation, or as a system, sorry, we write this as a matrix equation. Okay, recall from the previous lecture, you have a linear system, you can write it as a matrix equation. So this guy here can be written as you have UV, this is equal to A, B, C, D multiplied to the vector X, Y. Okay? If you don't believe this, then try to multiply this. The first entry will be AX plus BY. So the first entry will be U. And that's what we have here. For the second entry, you have the second row, C times X plus D times Y. And that's equal to V. And we have it here. Okay? So what we're going to do is the following. First, we will assume that AD minus BC, this is not equal to 0. Okay? The reason is, later, if you try to solve this as a linear system without using the matrices, this guy here will appear. The number AD minus BC will appear. Okay? So we will need to assume this. AD minus BC not equal to 0. Okay? So we let A be the matrix A, B, C, D here. Okay? Because AD minus BC not equal to 0, we can solve for the inverse of A. Then A inverse, this is 1 over AD minus BC. And then here, you will have D and A. So you interchange the diagonals. Then here, you negate the other entries. Okay? Or if we put this scalar inside, we will have the following. You have D over A D minus BC, and then minus B over AD minus BC, minus C over AD minus BC, and then A over AD minus BC. Okay? Following? Then, take note, we have this here, UV, it's equal to this matrix times this vector. So what we're going to do is to multiply A inverse on the left, okay? Left factor. So what does that mean? I will have A inverse times this vector UV here. This should be equal to A inverse times A, B, C, D, B, C, D, and then times U, V. Sorry, it's XY on the right here. You have X, Y. So take note, if we consider the grouping, you have this grouping first. Correct? And then if we regroup this is equal to what? You have A inverse times your matrix A, B, C, D. Okay? And then you have here X, Y. Correct? But then again, this guy here, this is your matrix A. Well, it's this guy. And you have inverse of A times A. You should get the identity there. Okay? So this guy here will be equal to the identity, the 2 by 2 identity matrix. Or let me write it like this. 1, 0, 0, 1. That's your identity matrix. That's the property of inverses. You have a matrix A which is invertible. You multiply it with its inverse. You should get the identity matrix. And this is X, Y. Okay? But if you multiply these two guys here, you will have X, or you have 1 times X, that's X, plus 0 times Y. So you'll just have X here. And then in here, 0 times X, that's 0, plus 1 times Y. So you'll just get Y here. Okay? So at the very least, your right-hand side now is just in terms of X and Y, and there's no other, there are no other terms. This guy here, well, all we need to do is to multiply this A inverse times the vector UB. Okay? So I'll put the computation in here. Okay? So you have X, Y. This is equal to, let me write the inverse of A. That's D over AD minus BC. This is negative B over AD minus BC. Here we have negative C AD minus BC, and then A over AD minus BC. And then you multiply this to the vector UV. So, well, if you convert this to a matrix, or to a linear system, or to equations, you will now get, so X equals this guy times U plus this guy times V. Okay? So D over AD minus BC U minus B over AD minus BC V. That's for X. Then for Y, you have negative C over AD minus BCU plus A over AD minus BCV. So this is what we want. Okay? questions? Okay. Now, let us look at some properties. Suppose you have two invertible matrices of the same size, A, B, right? Then the product, A, B, is also invertible. And then the inverse can be calculated this way. So you have a matrix A which is invertible, you have a matrix B which is invertible, you multiply them, the product will also be invertible, right? And to calculate that, you can just multiply the inverses of your two matrices. But take note of this guy here. On the left-hand side, you have product AB. So A is on the left, B is on the right. Then you get the inverse of that. When you multiply the inverses of A and B, your left factor will be coming from the B. So you have B inverse here. Then the right factor will be the A inverse. Okay? So they will interchange. Okay? So again, if A and B are invertible matrices of the same size, then AB is also invertible, and the inverse will be calculated this way. Okay? So for example, you have this A and B. Okay? These two guys here, they are invertible, and we've calculated them. So anyway, let's have the inverses first. A inverse, this is equal to 1 over, we haven't calculated the inverses of this. But anyway, let's calculate now. A inverse, it's 2 times 1 over 2 times 1 minus 4 times negative 3. Okay? And then here, we interchange 1 and 2. So this becomes, interchange 2 and 1. So this becomes 1, 2. And then you negate 4 and negative 3. So this becomes negative 4 and this becomes positive 3. Okay? Then let's simplify this. You have 4 times negative 3, that's negative 12, but we have negative here. So 2 plus 12, that's 14. So this guy here will be 1 over 14, 3 over 14, negative 4 over 14, 2 over 14. So I'm not simplifying these fractions here. Okay? So this is the inverse of A. The inverse of B, we have 4 times 1 there. So 1 over 4 times 1 minus 1 times negative 1. 1 times negative 1. Then we interchange. So 1, 4 here. And we negate. Negative 1, 1 here. So if we simplify this, 4 minus negative 1, so 4 plus 1, that's 5. So we will have here 1 over 5, and then 1 over 5, negative 1 over 5, 4 over 5. Okay? Next, let us calculate AB. So let us multiply AB. We have here 2, negative 3, 4, 1. And then we multiply to 4, negative 1, 1, 1. I think this guy here we've solved. So let me just look at that again. It's this guy here. Oops, not that. Where is that? This. So 2, negative 3, 4, 1, 4, negative 1, 1, 1. This is the inverse. 5, negative 5, 17, negative 3. Okay? So let me just get that. So 5, negative 5, 17, negative 3. So here you have 5, negative 5, 17, negative 3. Okay? So if we calculate the inverse of this, so AB quantity inverse, this will be what? 1 over 5 times negative 3. So 5 times negative 3 minus 17 times negative 5. Okay? And then this guy here, we interchange 5 and negative 3. So you will have your negative 3 and 5 here. And then we negate. Okay? So we have negative 17 and then positive 5 here. So if we simplify this, let's just have what? Let's calculate this denominator. So you will have negative 15 plus 17 times 5. That's 85. Correct? So this is equal to 70. Okay? So 1 over 70 for that. Okay? So 1 over 70, or we will have negative 3 over 70, 5 over 70, negative 17 over 70, 5 over 70. Okay? That's your AB inverse. And then we now calculate B inverse A inverse. B inverse A inverse. So B inverse A inverse. So we have here for the B inverse, it's this guy. So 1 over 5, 1 over 5, negative 1 over 5, 4 over 5. Multiply it to A inverse, which is 1 over 14, 3 over 14, negative 4 over 14, 2 over 14. So if we do this, we will have 1 over 5 times 1 over 14. 5 times 14, that's 70. So this is 1 over 70 plus 1 over 5 times negative 4 over 14. So we will have negative 4 over 70. And as you can see, 1 minus 4, that's negative 3 over 14. So at least for this entry, we are correct. But you will see all of these terms will appear. Next, you have 1 over 5 times 3 over 14. So you have 3 over 70 1 over 5 times 2 over 14. So that's plus 2 over 70. And that's your 5 over 70 here. Okay? And then second row, first column, negative 1 over 5 times 1 over 14. That's negative 1 over 70 plus 4 over 5 times negative 4 over 5. That's negative 16 over 70. And that's your negative 17 over 70. Then lastly, we have here negative 3 over 70. And then here 8 over 70. So plus 8 over 70. So you will get this. So AB inverse equals B inverse A inverse. Okay? Now, I want you to check. Try to solve. So solve A inverse B inverse. You have here your A inverse, you have here your B inverse, so you just multiply this and this using this arrangement. And try to check if you will get the same as this. Okay? Take note, I told you, in general, you cannot just interchange the locations of your factors in the multiplication. So this guy here, possibly it's this guy, but also there's a possibility that it's not this guy, but we don't care. Okay? If it is not this guy, then that just proves that you just don't distribute the negative here, the inverse symbol here. Okay? Okay? Questions? Now, since we have these inverses, some students think that this guy here, it's a power of a matrix. Okay? But this guy here, the negative one in as an exponent, quote unquote, okay, of a matrix, it means you are getting the inverse. Okay? It means you are getting the inverse. And I already mentioned that A inverse, this A inverse here, we will not write it as 1 over A. Okay? If A is a matrix. Okay? So this guy here will not make sense to us. Okay? So, with that, let us look at some powers of matrices. Suppose A is a square matrix. We will define this A to the power 0. Okay? A to the power 0, that's your identity matrix. Okay? And then, of course, if you have A to the power n, where n is a positive integer, it's just that you multiply A with itself n times. So you have A times A times A until times A, where you have n factors of A. Okay? What about now if you have negative exponent? Okay? If A is invertible, A raised to negative n, this means you are multiplying A inverse with itself n times. So you have here A raised to negative n. This is A inverse times A inverse times A inverse and so on. And you have n factors. Okay? So in here, of course, n is a positive integer. So this guy here, it means that you have A inverse raised to n. This one is the same as this. Okay? Question so far? And then from here, for any non-negative integers R and S, so they are integers and non-negative, we can also do this. A to the R times A to the S, it's the same as A to the power R plus S. Very much the same as a property as the laws of exponents of real numbers. And in here, you have A to the R, then you raise it to S. It's the same as A raised to R times S. Okay? Questions? So these properties here, you've seen this in the set of real numbers. So they still hold. Okay? They are still true for matrices. Next, suppose A is invertible and n is a non-negative integer. The inverse of the inverse of A, that is equal to A. So in here, you have inverse A. You get the inverse of that, you should get A. You should bring back the matrix A. Now, A to the n is also invertible. So again, A is invertible, n is a non-negative integer. So you multiply A with itself n times, that will still be invertible. So the inverse of A to the n, so it's this guy here, it's just A inverse multiplied to itself n times. So it's like you can multiply the n with the negative 1. That's why you have here A raised to negative n. And then this guy here, you have A inverse raised to n. Okay? Now, if you get a scalar, a non-zero scalar, you multiply it to A, then the product Ka is also invertible. When you get the inverse of this, okay, so you have the product Ka, you get the inverse of that, you have here K raised to negative 1 A inverse. Take note that in this case, since K, this is just a number, this is just a number, this is also the same as 1 over K A inverse. This guy here, 1 over K, it makes sense to us because K is just a number. Okay? It has this guy here, 1 over K, we will know that. 2 raised to negative 1, that's just 1/2. So you can do that for scalars. But for matrices, you cannot put the matrix as a denominator of some certain division, which is, that's not valid. Okay? Okay. So let's look at this. Okay? You have the matrix A, then you want to find A squared, A raised to negative 2, and then you have A inverse squared. Actually, this guy here, it's the same as this guy. But what does this mean? You have A inverse, you raise it, you multiply A inverse with itself. Okay? But anyway, since these are two the same, okay, you'll just have one, um, you just have one solution to that. Actually, you can have two solutions, okay? By this here, maybe let's try to solve it this way. You have A squared inverse, okay? And then we verify that this guy A squared inverse, it's the same as A inverse squared, okay? So first, let's have A squared. So this is negative 2, negative 3, 3, 4. You multiply it with itself. Negative 2, negative 3, 3, 4. So we will have negative 2 times negative 2, that's 4. Negative 3 times 3, so that's minus 9. Okay? And then we have negative 2 times negative 3, that's 6. Negative 3 times 4, that's minus 12. 3 times negative 2, that's minus 6. 4 times 3, that's 12. So plus 12. 3 times negative 3, that's negative 9. 4 times 4, that's positive 16. So plus 16. So this guy here, 4 minus 9, that's 5. Sorry, that's negative 5. 6 minus 12, that's negative 12. Minus 6 plus 12, that's positive. Sorry, 6 minus 12, that's negative 6. So negative 6. And then negative 6 plus 12, that's positive 6. Negative 9 plus 16, that's positive 7. So obviously, you don't square the terms, okay? If you square this is positive 4. But notice, the actual value should be negative 5. So you just don't square it. You have to do the multiplication, okay? This is your A squared. And then let's calculate A inverse or A squared inverse. So A squared inverse. So we have this. We have 1 over negative 5 times 7 minus 6 times negative 6. 6 times negative 6. And then here we interchange. So this is 7 here. This is negative 5 here. Then we negate the other terms or the other entries. This is negative 6. This is positive 6. So anyway, simplify the denominator. Negative 5 times 7. That's negative 35. 6 times negative 6, that's negative 36, but there's a minus here. So you'll just have 1 over 1. 7, 6, negative 6, negative 5. Or simply, you have this guy here. So 7, 6, negative 6, negative 5. So this is A squared inverse. Okay? Now, let's look at A inverse first. So A inverse, this is 1 over negative 2 times 4 minus 3 times negative 3. Oops, multiply to the matrix. Interchange. So 4, negative 2. Negate. We have negative 3, 3. And then negative 2 times 4, that's negative 8. 3 times negative 3, that's negative 9, and therefore you have a minus here. And since you have a minus here, you'll just have 1 as a denominator. So A inverse, it's 1 over 1, 4, 3, negative 3, negative 2. So this is your A inverse. And then if you square this, you should get this matrix here. Let's calculate. A inverse times A inverse. We have here 4, 3, negative 3, negative 2. 4, 3, negative 3, negative 2. This is equal to 4 times 4, that's 16, minus 3 times negative 3. So, sorry, 4 times 4, that's 16. 3 times negative 3, that's minus 9. That's why we have here 16 minus 9. And then for the entry here, 4 times 3, that's 12. 3 times negative 2, that's 6, so minus 6. Then here, negative 3 times 4, that's negative 12. Negative 2 times negative 3, so that's plus 6. And then negative 3 times 3, that's 9. Negative 2 times negative 2, so that's plus 4. Sorry, negative 3 times 3, that's negative 9. Negative 2 times negative 2, that's 4. So, yep, you will get 7 here, 6 here, negative 6 here, negative 5 here. So, it's the same as this guy here. Okay? Questions? Okay. Next. Suppose we have an n by n matrix A. Right? And suppose P is a polynomial of degree m. Say your P of x can be written as A sub 0 plus A sub 1x plus until A sub m x sub x raised to m. Okay? Then we can also evaluate this polynomial at a given matrix. Okay? So we will define the matrix P of A. So this P of A to be the matrix given by this. A sub 0 times the identity matrix plus A sub 1 times the matrix A plus A sub 2 times A squared until A sub m times A raised to m. Okay? So to understand this better, suppose you have this matrix A, negative 3, negative 2, negative 3, 3, 4. That's the same matrix that we have in the previous slide. Okay? And suppose our polynomial it's p of x equals x squared minus 3x plus 2. We want to find p of a. So according to this definition, your p of a, this is simply a squared minus 3a plus 2 times the identity matrix. Okay? So if we have this, what is your a squared? Our a squared, let us look at the previous slide. This is our a squared. Okay? This is our a squared. Negative 5, negative 6, 6, 7. So here we have negative 5, negative 6, 6, 7. So let me just write this from previous slide. From previous slide. Okay? Then we have minus 3 times the matrix A here. So negative 2, negative 3, 3, 4. Then plus 2 times the identity matrix. It's 1, 0, 0, 1. Okay? And therefore, let's just simplify this. Okay? We have here negative 5 minus 3 times negative 2. Okay? So we will have plus 6. And then plus 2 times 1, so plus 2. For the entry here, 6. Then minus 3 times 3, so that's minus 9. Plus 2 times 0, that's just 0. For the entry here, we have minus 6 plus 3 times plus negative 3 times negative 3, so that's plus 9. Plus 2 times 0, that's again 0. And then for the entry here, you have 7 plus negative 3 times 4, that's minus 12, plus 2 times 1, so that's plus 2. So if we simplify this, we have negative 5 plus 6, that's positive 1, plus 2, that's 3. Negative 6 plus 9, that's 3 again. 6 minus 9, that's negative 3. 7 minus 12 plus 2, that's negative 3. So this is the polynomial P of A. Okay? Questions? Some more properties of inverses and transpose. Okay? So remember, you have transpose before. Okay? So suppose the sizes of the matrices are such that the stated operations can be performed. Then we have these properties of transpose. So A transpose transpose, this is equal to A. So you have a matrix, you transpose it, and then you transpose it again, you'll get the matrix A back. And then here, you have two matrices. If you add them, then you get the transpose. it's equal to adding the transposes of your matrices. So it's like you can distribute this transpose thing. Similarly, if you have difference, so A minus B transpose, it's A transpose minus B transpose. If you have a scalar multiplied to matrix A and you get the transpose of that, it's the same as it's the same as multiplying the scalar to A transpose. So K is not affected by the transpose. Okay? And then you have two matrices which you can multiply. Okay? You multiply them. So you have matrices A, B such that if you multiply A and B, it exists. So the product AB, if you transpose that, it will be equal to B transpose A transpose. So similar to the inverse. You cannot just distribute this exponent or this superscript. You have to interchange the factors. So AB transpose, it's equal to B transpose A transpose. Okay? Now, if we combine inverse and transpose, so suppose A is invertible, and then A transpose will also be invertible. Okay? And furthermore, the inverse of A transpose, it's equal to the transpose of A inverse. So you can interchange these two operators. Okay? You have A, you transpose it, you get the inverse, you will get some matrix. That matrix will be equal to, you have A, you get the inverse first, and then you transpose. Okay? So A transpose inverse, it's equal to A inverse transpose. So, for example, we have these two matrices again. Okay? Let's just work on the matrix A. And then I will leave to you the matrix B to verify this identity here. Okay, so I'll just be working on the matrix A. So for the matrix A, let's start with A transpose. So transpose, rows become columns, and columns become rows. So row 2, -3 becomes the column 2, -3 here. And then the row 4, 1, it becomes the column for 1 here. Then let's get the inverse of this. So A transpose inverse, this is 1 over 2 times 1 minus -3 times 4. And then here, we interchange 2 and 1 here. So this becomes 1, 2. Then we negate. So this becomes +3 and -4. And then this guy here, it's 2 plus 12. Correct? So that's 14. So we have here 1 over 14. And then -4 over 14. 3 over 14. And then 2 over 14. So this is A transpose inverse. Okay? Now, let's start with the A inverse. So you have A inverse here. and that's equal to, so this is our A. We still have 1 over 2 times 1 minus negative 3 times 4, that's still 14. But this time here, you interchange 2 and 1, so we have 1, 2. You negate these two guys, so you have negative 4, positive 3. So if we simplify this, you have 1 over 14, 3 over 14, negative 4 over 14, 2 over 14. So this is the inverse. If we get the transpose of this, so A inverse transpose, this row here becomes a column. So we have 1 over 14, 3 over 14. This row here also becomes a column. So negative 4 over 14, 2 over 14. And that's precisely this guy here. Okay? So at least using this example, this guy here is true. And of course, in general, it is true. As long as your A is invertible. Okay? So try to work on the example, the matrix B. Okay? Try to verify this guy here using the matrix B. Okay? Questions? Okay. Let's have some more examples here. We have these two guys. Okay. So we want to find the matrix A if 7A inverse it's equal to this guy. Or if we have here 5A transpose inverse, it's equal to this guy. Okay. So for these two examples, I will not put this on the record. Okay. So you can work on this. So if you're gonna work on this problem, just hit pause and then you start working. Next, let's have this example. Find the matrix X if it satisfies this equation. Again, we will let this to be the matrix A. Okay? And now, we have determinant of A. This is 1 times 1. So 1 times 1 minus negative 1 times 1. So this is equal to 2. Okay? Therefore, A is invertible with A inverse, let's calculate that. A inverse, this is 1 over 2 times, we interchange. This is 1, 1. And then we negate the other entries. This is 1, this is negative 1. So that we will just have 1 half, negative 1 half. And then here, you have 1 half and then another 1 half in here. Okay? So what's the deal if A were invertible? So you got AX equals 2 times the matrix 1, 4, 3, negative 5, 2, 6. Since A is invertible, what we can do is to multiply A inverse on both sides of the equation on the left. Okay? 2 times this matrix here. 1, 4, 3, negative 5, 2, 6. And left-hand side, it's just A inverse A times X. For the right-hand side, let's write the matrix A inverse here. So you have 1 half, negative 1 half, 1 half, and then 1 half here. And then you have 2 times, again, the matrix 1, 4, 3, negative 5, 2, 6. And therefore, remember, A inverse A, that's just the identity matrix. So you just have I2 here, X, because you have a 2 by 2 matrix here, or you will have the X. Okay? And then for this guy, this 2 here, it's a scalar, so you can just multiply this scalar on this matrix. So you will have 1, negative 1, 1, 1. So this is multiplied to 1, 4, 3, negative 5, 2, 6. And for you, as an exercise, try to multiply this and you will get the X. Okay? So, our next examples here, we have some proving and another proving here. And the rest of the slides will be exercises. So I'll do the proving on our next video. So on our next meeting. But for now, I want you to practice on the exercise that I left. And that would be all. Thank you. So I hope you've learned something new today. Bye-bye.